Let's take the polarizability, which we had defined as the second derivative of an energy with respect to alpha was the minus the second derivative of the energy in the presence of an electric field with respect to two components of that field, alpha and beta, and then evaluated at zero field strength. So that's precisely an example for this one here, except that this is an electric field, and for the electric field there is no second order Hamiltonian contribution. So this term we don't have at all, because there is no second order Hamiltonian, so we only have this one. And you can see the derivative of the first order Hamiltonian with respect to the field, that's the alpha or beta component of this PF operator here. And that PF operator was minus the dipole moment operator. So we get, here we get the beta component of the dipole moment operator, here we get the alpha component, the alpha and the beta component. And everything is real, so I really get minus 2 times the same term. Sum over n not equals to 0, and then I get psi 0, and I get, now 1 minus here, 1 minus there, gives me a plus, so I just get the dipole moment operator, the alpha component, psi n, the beta component of the operator, psi 0, divided by the energy difference. And this mu is in principle both contributions, electronic and nuclear, because that's the dipole moment operator. And here it is. But what happens with that nuclear contribution here? What do I integrate in that integral up there? What are the variables I integrate over? The electronic coordinates. And that nuclear contribution to the dipole moment, that depends on? Nuclear coordinates. So with respect to the integration variables, this is, with respect to the electronic coordinates, this is a constant. So what I do here actually,
take the derivative.
Right. So what I do here, I basically just take that out. So 0 mu alpha electronic psi 0, and then I could write the same with the nuclear one, but I can take the nuclear out of the integral, and then I have the overlap between the psi zeros. And this is the same state, same function, and they are normalized. So this is 1. So I get this plus just the alpha component of the nuclear, which I can calculate just from the coordinates of the nuclei. Now I can do the same here, or I have to do the same here. I can split it up in an integral over the electronic one and an integral over the nuclear one, and the nuclear is still a constant with respect to that integration, so I take it out. But now I have the overlap between psi 0 and psi n. And those are the eigenstates of my zeroth order Hamiltonian, and they are orthogonal. So this integral, this overlap integral is 0, and therefore there is no nuclear contribution. This is just the electronic one. If you do Born-Oppenheimer, where we have the nuclear coordinates fixed and we only deal with electronic wave functions, which is actually only the first part of Born-Oppenheimer approximation, there is no nuclear contribution here. There will be something when we do the second step and bring the nuclear wave functions in again, because then the nuclear operator is no longer a constant. But this is just the electronic ones. Now, what is the sign of the diagonal? This is a tensor having in principle 9 components. But you can see, I mean, it's symmetric. It's the same operator. If I have alpha beta or beta alpha, that doesn't make any difference because I used that already in order to get the 2 here. So that's a symmetric tensor. It has only 6 unique elements. If I look at the diagonal elements having alpha and alpha, what is the sign of a diagonal element of the polarizability? Is it positive or negative? This is negative because it's E0 minus one of the higher states, and which cancels the minus sign here. And then, at least for the diagonal elements, I can be sure about it because then I have just this one squared. And that's going to be a positive number. So they are positive.